This lesson is on heating and cooling curves. To do these problems, you will be using all the knowledge you already know about calculating specific heat and delta H of fusion and delta H of vaporization. So, quick review of a heating and cooling curve, which you saw in the last video. The delta H vaporization and fusion video. On the curve, you're going to see temperature on the y-axis, heat or energy on the x-axis. As the heat is added, temperature goes up, so you can see the line. You get this diagonal line as it goes up. I'll do it in green so you can see it. And then when you get to a horizontal part, that would be a phase change. And then it goes up again, temperature goes up as you add heat. You're going to hit another phase change, and then the temperature is going to increase again to whatever temperature you stop at. In here, you can split the sections. So you could say the first increase to the first phase change, we call this usually section 1. Then that first phase change, your fusion, your melting or your freezing, depending on the direction you're going in. This would be section 2. Your increase to the next phase change would be section 3. Your second phase change, vaporization, so boiling or condensing, again, depending on which direction you're going, adding or removing heat. This would be section 4, and then any increase above that in temperature would be section 5. In sections 1, 3, and 5, if you wanted to calculate the heat, you would use your specific heat equation because you have a change in temperature. So Q equals M times delta T times the specific heat of whatever your substance is. If you were calculating the heat in sections 2 and 4, you would use the equation Q equals N times delta H, and depending on your section, it'd either be fusion or vaporization. So what we're going to be talking about in this video is how to calculate the total heat. And the total heat would be adding up all of the sections for whatever temperatures you're going from. For instance, if you were going from below the melting or freezing point, temperature-wise, so somewhere over here, all the way up to a temperature above your vaporization point, you would add up the heats calculated for sections 1, 2, 3, 4, and 5. If you were calculating only from, let's say, somewhere between the melting and boiling point, like here, and then up to that temperature above your vaporization, you would add together the sections 3, 4, and 5. So only the sections that exist within your temperature range. So it'd be the sum of all sections. So there really is nothing new in this video. It's calculating the same things you've already been practicing. Now it's just putting them together and adding them up. So let's do an example problem. So pause here, write the problem down, and we'll go through it. So the problem reads, to calculate the energy in kilojoules, make sure you note the unit, required to heat 25.0 grams of water from negative 30 degrees Celsius to 110 degrees Celsius. So we're actually going to go through all 5 sections. So in doing these problems, it might help to make a small sketch of what the graph would look like. Okay, if we're going from negative 30, okay, at 0 for water is where you're going to have, let's see, we're adding heat, so we're going to melt here. And then the temperature is going to increase once it's all melted up to 100 degrees. And there you're going to have your boiling. And then after that, you're still adding more heat because this is going to go up to 110. Okay, so we have 5 sections. So in order to find the total heat, calculate the energy, we're going to need to calculate the energy at each specific section, 1 through 5, and then add them up. So I'm going to write out some of my givens to help me out. My mass was given to me as 25.0 grams. I'm going to use mass in my specific heat equation, but I'm also going to need to know moles. So I'm going to right now calculate my moles, which is going to be 25.0 grams. I'm going to convert grams to moles. So for every 1 mole, we're talking water here. The mass is 18.02 grams per mole. So the moles are 1.39. Okay. I'm also going to write down for our purposes to help ourselves out all the constants we're going to use, so the specific heats and the delta H's. So the specific heats are all on page 533 for water and a bunch of other things, but you're going to need to know the specific heat of a solid, because we're talking ice, so this will be in section 1, and that is 2.06 joules per gram degrees Celsius. The specific heat of a liquid, so in section 3, is 4.184 joules per gram degrees Celsius. And the specific heat of gas is 1.87 joules per gram degrees Celsius. And that would be section 5. The delta H's you're going to have to use for sections 2 and 4. So the delta H of fusion for water is 6.01 kilojoules per mole. So that's going to be section 2, fusion. Section 4, we're going to need the delta H of vaporization, and this is 40.67 kilojoules per mole. Remember, it takes more energy to convert from a liquid to a gas because they are more different than a solid and to a liquid. All right, so now we can start our problem. The key to these problems is being organized and knowing all your Q values so that you can add them up at the end. So I label all my sections. So I'm going to write section 1. This is where I have solid water. And my temperature change, we're going to have to calculate here for this section. We're going from -30 up to 0. So 0 is our final temperature minus our initial -30. Oops, I should be using sig digs. Now this 0 is 0.000 repeating. It's exact. All right, so we're going to look at for our number, we want the lowest numbers of digits after the decimal, which would be 1 from the 30.0. So subtracting a negative would give us positive 30.0 degrees Celsius. So we can calculate Q. So Q1 is the mass times the change in temperature times the specific heat of a solid. So our mass was 25.0 grams times our change in temperature, 30.0 degrees Celsius, times our specific heat of a solid, which was 2.06 joules per gram degrees Celsius. So you can see grams divide out, degrees Celsius divide out. Answer is, with 3 sig digs, 1,550 joules. But we want to calculate our energy in kilojoules, so I'm going to convert this right now. Moving the decimal 1, 2, 3 spots to the left. So this would be 1.55 kilojoules. I'm going to underline this. This is one of the numbers I'm going to use when I add them up. All right. Second section is, if we go back up to our graph, is the fusion. So number 2. So we've done 1. Now we're on 2. So we're going to use the delta H of fusion and the moles. So 2 would be melting. So Q2 is N times delta H of fusion. So 1.39 moles times 6.01 kilojoules per mole. Moles divide out. So here we get 8.35 kilojoules. Again, I'm going to underline it, so that's my second number to add. Section 3 is when it is a liquid. So here the temperature is increasing, so we have to calculate our change in temperature. We're going from from 0 to 100, so we're going to do our final 100. And like I said before, it's going to have as many sig digs as we need as exact, minus 0. So this will be 100 degrees Celsius. I'm just going to put the 0.0 for extra sig digs. I won't need 4. My other numbers don't have 4. So now I can calculate Q3, which is the mass times the change in temperature times the specific heat. So 25.0 grams times 100 degrees Celsius times 4.184 joules per gram degrees Celsius. So grams divide out, degrees Celsius divides out. And here we get, with 3 sig digs, 10,500 joules. And I'm going to move my decimal, convert right away to kilojoules. So this is 10.5 kilojoules. Section 4, we're looking at boiling here, or vaporization. So we don't have a temperature change, so we're going to use Q4 equals N times the delta H of vaporization. So 1.39 moles times 40.67 kilojoules per mole. So here we get 56.5 kilojoules. Oops, I didn't underline these. So we've got 4. We're almost done. Our 5th section, if you're going back up, so we did 3 was a liquid, 4 was boiling. Now we're going to do 5. We're at a gas. So we have a change in temperature, so we're using C sub P of a gas. So we need to calculate our change in temperature. Our final temp is 110. It's coming from 100. So 110, 0.0 minus 100. We'll keep the same number of sig digs. So this would be 10.0 degrees Celsius. So Q5 equals M times delta T times C sub P of a gas. So 25.0 grams times 10.0 degrees Celsius times 1.87 joules per gram degrees Celsius. Grams divide out, degrees Celsius divide out. So here we get 468 joules, which would be 0.468 kilojoules. All right, so we've now calculated the heat for every section. So now it's to find the total heat. So the total amount of energy is going to be Q1 plus Q2 plus Q3 plus Q4 plus Q5. So in adding them, they have to be in the same units, so I already converted them all to kilojoules. So 1.55 kilojoules plus 8.35 kilojoules plus 10.5 kilojoules plus 56.5 kilojoules plus 0.468 kilojoules. Okay. Your answer, since we're adding, we're looking at lowest numbers of digits after the decimal, which is 1. So my answer would be 77.4 kilojoules of heat. That's how much is added to the water, 25 grams of water, to get it to increase from -30 degrees to 110 degrees.